Hello, everyone. Okay, so last time in class, we discussed merge sort. Let me remind you what's this merge sort algorithm. So it's an algorithm for sorting array, let's say array of numbers. And the way it goes, it's a recursive algorithm. I'm reminding you, okay? We talked about this already, but I'm just reminding you. The way it works is it gets an array of n elements, and it first sorts one half recursively, then the other half recursively, and then we saw this merge algorithm that runs in linear time in n. Okay, so this half is sorted, this half is sorted, and then we found a way how in linear time merge these two halves into one array that's fully sorted. And we said the running time of this uh, it's 2 times t n over 2, right? So we have two recursive calls plus order n for the merge. And we would like to analyze it. So we saw one analysis in class last time, but I will show you another analysis. So here is how it goes. The proof will be by induction. So suppose T of n is 2 times T of n over 2. These are the two recursive calls plus T of n. And let's say T of 1 is just 1. And we'll prove by induction that T of n is at most, so if this is our constant C, maybe C is like 3 or 4 or something, then T of n is at most 2 times C n log n for all n greater than 2. Okay, that's the claim, and we'll prove it by induction. So the way induction works, we first show it for a base case, say n equals 2 in this case. So for n equals 2, what's the running time for n equals 2? So we make two recursive calls, so it's 2 times t of 1 plus c times n. So c times n is 2 times c. So we sum this up, and when n equals 2, we indeed see that t is less than 2 times c n. Okay, so when n is 2, so less than 4 times c. Right. So this is the base case of induction. And then we say, suppose that the claim holds for lengths less than n, and we prove it for n. So here is how it goes. So let's see. What's t of n? Just by what we said, it's two recursive calls of size n over 2 plus c times n. Let's see. By induction, what can we say about t of n over 2? It's at most 2 times c, I'm just copying it from here with n over 2. 2 times c times n over 2 plus log of n over 2. And I'm just copying this, the merge part of the entire thing, c times n. Okay, let's see. So what's going on here? So we have 2 times 2c times n over 2, so it's just, multiply by 2, divide by 2, so it's 2 times c times n plus times log of n over 2 plus cn. Okay. Next step, note that log base 2 of n over 2, if you remember your rules of logarithms, just log base 2 of n minus 1. All right, and this is the rules of logarithms. And, we have plus c times n minus 2 times this, so it's strictly less than 2 times c of n log n. Okay, so this is exactly what we wanted to prove, right? We started with t times n, no, this is definition, and we said that it's less than this, which is exactly what we wanted to prove. So yeah, these proofs by induction, I actually don't really like them because, there is the claim, okay, we do the base case, we do the inductive step, but I don't know if we actually learn anything other than verifying the arithmetic with. Anyway, but this is another proof. Okay, so that's what we have for the induction. Proof by induction that the running time of merge sort is indeed upper bounded by n log n. Let me give you one more analysis. So it's kind of different analysis. And I feel there's something more intuitive going on. Okay, so notice that in merge sort, what's going on there? So there are the induction calls, given two recursive calls on n over 2, which is, basically doesn't do much except for making recursive calls. And all the work is actually done in the merge part. So in the merge part is, what's the running time of the merge part is each element is being copied once. It's copied into a new array and then being copied back. if you remember how merge sort works, right? So we had these two pointers. Each time we choose one of the elements, copy them into this new array, and then copy it back into our array. So the total running time is essentially the number of times all elements are being copied together. So, if we count for each element how many times it was copied back and forth, so it should be number of times. If we do it for each element, if we count for each element how many times it was copied in this merge procedure, this is essentially the total running time. Okay. So let's count the number of time an element is copied in all merged parts in total. And if we do that, then we multiply by n, because we have n elements, this will be the running time. So here is a claim. Each element, so if we start an array of length n, each element is moved at most log n times. And the reason is the following. So, for one merging procedure, an element is moved exactly once, right? Because for one merging procedure, we have these two half arrays, we move them into a new array and then copy back. So maybe it's twice, if you count it, copy into a new array and then copy back. Or let's say it's just, we call it once. So here is a question. Look at a particular element, A in position 9. In how many different merging procedures does it appear? Well, let's see. First, it appears in the merging procedure for length n, right? Then we divide the array into two halves, and this element appears, either in this half or in this half. So then it appears in the merging procedure of half the size, and then in the merging procedure of quarter the size. So the size of the array containing the element, is divided by 2 each time, and we start with n, length n, and this element appears in the thing of length n, and then in the subarray of length n over 2, I don't know, in this size or in this side, but in one of the sides of length n over 2, and then this element appears maybe in the smaller part, so it will be n over 4, and then n over 8, and so on. So the total number of times an element appears in these merging procedures is log to the base 2 of n, because each time we divide by 2, the length of the array where this element lives, and then apply a merging procedure. So the point is we touch each element log n times, and we have n elements, so the running time is order n log n. Okay. And let me show you one by picture. So what are we seeing here? So, the total running time on input of length n, on the array of length n, is 2 recursive calls of length n over 2 plus another n for merge. So it's not really n, it's 5 times n, but let's pretend it's n just for simplicity. If it's 5 times n, then we'll write 5 everywhere. Okay, so I pay n for the merge of the long array, the entire array. Then we'll make 2 recursive calls. Okay, so this is one recursive call, this is another recursive call, and I pay n over 2 for merge of this half and n over 2 for merging this half. But each of these halves also has a recursive call, to quarters. And in each quarter, we pay n over 4 for the merging of this quarter, and then we go, another step down in the recursion. There's 2 more smaller recursive calls. Okay? Until at the very end, we reach the base case of the recursion where the arrays are of length 1. So if we sum up all these numbers together, this will give us the total running time. Let's see. What's the total running time? If we count the time layer by layer. So in the first layer, the total running time is n. In the second, we have 2 halves, each of size n over 2, so it's also n. Then in the next one, we have 4 quarters, each of length n over 4, that's also n, and so on. So in the next one, we'll have 8 parts, each of size n over 8, so that's also n, and so on. And how many layers do we have? So look, we start with n and divide by 2, divide by 2, divide by 2, divide by 2, until we reach subarrays of size 1. So we have log n many layers. In each layer, we pay order n time, which means the total running time is n log n. Okay, I hope, okay, so we saw three different proofs. One is by induction. One is, by counting how many times each element is being touched. And this third using this, tree that expresses the running time in each layer. I hope this convinces you that the running time is order n log n. Right, so here's the conclusion. Merge sort runs in n log n time, and one downside of this is that we need of an extra memory. And let me mention one open problem. Uh, I think it's open. I don't know how to solve it. Okay, a problem. Uh, Implement merge in O of n time and of on one extra space. So if you can do this, I would be very interested by this. Okay, so this. So we want the merge to run in linear time, but I don't want to pay extra space for it. Okay, so only constant number of bits are allowed. If you can do that, I think I would be curious about this. Okay, so this was about merge sort, and now we move on to our last sorting algorithm, which is called quicksort. And it's called quicksort because, for the obvious reasons, it's quick. So here is the idea of quicksort. So we get an array. Yeah, we have an array of length 100. We choose some element in the array, maybe, the first element or maybe the element in the middle or something, and we call it the pivot. And then we rearrange all elements so that all elements on the left will be smaller than the pivot, and all the elements on the right are larger than the pivot. Okay. So now, the array is not sorted, but we know that everything on the left of pivot is smaller than pivot, and everything on the right is greater than the pivot. Which means we can only recursively solve one half, recursively solve this half, and if we do this, then we get a completely sorted array. Okay, so it's different from merge sort in the sense that in merge sort, we first sort one of them, then the other, and then we merge them. And here we do something different. Here we first, do some rough sorting or whatever you can call it. Everything less than the pivot will be on the left, everything greater than the pivot will be on the right, and then we recursively sort. So it's in a different order, right? So we first do this rough, putting things on the left and on the right, and then we do recursive sorting. That's different from merge sort, where we first sort left and right, and then we merge them. Okay, that's your quicksort algorithm. And I didn't specify how to use a pivot, and sort of this part is not specified in quicksort, but let me give you some ideas. Maybe we choose just a random element. Maybe we choose the midpoint. And maybe we know something about the array, maybe it comes from a specific, maybe there's some information we have about the array, and we can choose a pivot wisely. So here is a question, for you, which pivots would be good pivots? And sort of jumping ahead, I will tell you good pivots are those that there's roughly half of the elements smaller than the pivot and half of the elements greater than the pivot. Okay, so we'll break the array into two halves, and then we'll make two recursive calls of size n over 2 roughly. Okay, and there is another question, how to rearrange the elements. So we chose our pivot, and we asked how to rearrange the elements. And let me present an algorithm. And let's say this is our array, and we choose 7. So we set pivot to be 7. And first, let's put 7 in the beginning. Okay. So it kind of, this is the first element in the array. It's right here, and we don't touch it anymore. Here's what we do next. We'll have two pointers, one pointing to the beginning, one pointing to the end. The left pointer will be going right, the right pointer will be going to the left, and here's what we do. We want the left pointer to always have small numbers and the right pointers to always have large numbers. So the left pointer will be moving to the right, and ideally it will have small numbers, no smaller than the pivot, and the right will be moving towards left, and ideally it will always have large numbers. Okay, so let me give you an example. So, one is happy because it has a small number. Then we move one step up. Oh, it has an 8. Oh, 8 is not good. 8 is large. So we stop for a second, and then we move the right pointer. So the right pointer is 3. 3 is smaller than 7. Okay. Oh, sorry. So 8 is greater than the pivot, so we stop. Now we'll take the right pointer. 3 is less than 7, but it only wants large numbers. So we'll stop again. Okay, let's see. 8 is too large, 3 is too small. How do we make them, nice again? How do we make the pointers happy? We swap 3 and 7. Now 3 will be a small number, right? So the left pointer is pointing to a small number, and 8 is a large number. And then we continue again. So our left pointer is pointing at 3, and then 4, and then it reaches 10. So when it reaches 10, it says, 10 is too large. That's not very good. Okay. Then we go to the right pointer. Right points at 8, 12. These are large numbers. 6. 6 is too small. That's not very good. Okay, so we found, left pointer pointing at a large number at 10, and right pointer points at 6, which is a small number. How do we make both pointers happy? We swap the numbers. Okay? And after we swap the numbers, the two pointers meet, which means, this is the end. And one last thing to do, we want to put the pivot between them so that everything on the left is small and everything on the right is large. Okay, so this was our algorithm for rearrangement. And what is the running time of this algorithm? Well, what's happening in every step? In every step, we either move the left pointer, or the right pointer, or swap. And notice that every element is, we pass on it exactly once, which means that the total running time is linear in n. Okay, and here's a claim. For good pivots, the running time is order n log n. And the reason is the following. So what's a good pivot? The good pivot is the one that splits the array into two equal halves. Why? Because if we split the array into two equal halves, then what do we have? A constant time for running a pivot, linear in n for rearranging, and two recursive calls. So if the recursive calls are on n over 2, then, this is exactly the same. Well, we can hide O of 1 inside O of n. And this is exactly the same running time, or exactly the same formula as we had for merge sort. And for merge sort, we saw that the running time is order n log n. So this means that if we have a good pivot, namely if it allows us to break the array into two halves, then the running time would be n log n. Good. And n log n, this is what we want from the sorting algorithms. And let me give you a different analysis. I like giving more than one, whenever possible to kind of show different ways of looking at the algorithm because, yeah, I want to show a different analysis of the running time for a good pivot, but I think it also says something about the analysis, about the algorithm. Okay, so what's really going on in quicksort? So we do rearrange, and then we make two recursive calls. So basically, if we count how many times each element is being touched, how many time in this rearrange process an element is moved to the other side or not moved, just passed by. Then if we do the sum over all elements, this will give us the total running time. The total running time is just how many times we touch the elements. Right. So here's an observation. Each element can be pivoted most once. It's a pivot, and then if it's a pivot at some point, after that with the recursive call on the left half, on the right half, so it can never be a pivot more than once. This element stays in place forever after it's a pivot. And here's an observation. Each element is swapped in this rearrange at most log n times. Why is that? Because I'm claiming that in each rearrangement procedure, we have these recursive calls, but in each, you fix one recursive call and you look at the rearrangement procedure for this subarray, each element is swapped at most once, right? Because the pointers say, move left, move right, move right, move left, and then swap. And after a swap, it goes to the next element, right? So each element is swapped at most once, and each element, I'm claiming it appears in at most log n many rearrangement procedures, because if it appears in one procedure, then we break the array into two halves. And our assumption, it's a good pivot. Namely, it allows us to break into exactly half. So each element will appear in only one of the halves. It cannot appear in both of them. So it appears in the entire array, and then maybe in half of them, and maybe in quarter, and 1/8, and so on. So we divide the length of the subarray that contains this element. We divide by 2 once and twice and 3 times, and no more than log n times, because after log n times, the array becomes just one element. So the conclusion is each element is touched at most one in each rearrange procedure, and we have at most log n rearrange procedures for each containing this element. So it means that each element is touched this many times, log n times, and we have n elements, so the total running time is n log n. Okay. So these were two different runtime analysis for quicksort with good pivots. Let me give you some exercises, just for practice. Let's say, we don't have an ideal pivot, but let's say our pivot is split 1/3 and 2/3. Can you show that the running time is still n log n? Okay, so that's your exercise. Let's say we have some way to choose a pivot so that it's not half-half, but 1/3, 2/3. Show that still the running time will be order n log n. Here's another example. Let's say that we have a terrible pivot. Okay, so it always chooses the maximal element. So it chooses maximal element, which means, the splitting is not very good. We'll have n-1 elements that are smaller than the pivot, and nothing will be larger than the pivot. So this rearrange costs us n. This is choosing the pivot. And this part is the recursive call. Okay, so it kind of gives you the answer, but convince yourself that in case we choose a maximal element, then the running time will be actually n squared. So, n squared is not very good, right? We saw these selection sort and insertion sort that run an n squared time. Okay, so here is a question for you. I said, if we can choose a good pivot, then we have a fast algorithm. But how can we choose a good pivot? And let me tell you several ways how to do it. So it turns out if we choose a random element, then just random element in the array, it's a pretty good heuristic. So it gives, with good probability, it will split the array nicely. Another way, maybe we don't choose even one element, but we choose 3 elements. And then, we have 3 elements like 1, 25, and 17, and we choose the one that's the median of them. So it's 1, 25, 17, so we'll choose 17 to be the median. Okay, so this will be our pivot. Oh, here's a really nice idea. How about we just compute the median? So the median meaning the elements such that half of them are greater than the median and half are smaller than the median. If we could do that, that would be amazing. How can we find the median? So one way to do it is, you sort the array, you get the array, you sort it, and then you just go to the element n/2, and this is your median. No, that doesn't work, right? So why doesn't it work? Well, look, our entire goal is to sort. So if we sort it, then we already done. So the median should cost less than sorting. The median should be done in linear time, and we don't know how to sort in linear time. Okay, so that doesn't work. But actually, it turns out there is a linear time algorithm for computing the median, although we will not do it in this course. And frankly, the running time there, yeah, it's linear, but the constant in this O, hiding in this O is pretty large, so it's not used in practice. I think the standard way to do it is just to choose a random element. I think this is a standard way to do it. All right, so just the conclusion. So quicksort for good pivots, the running time is n log n, which is amazing. Right, so it's more efficient than selection sort, insertion sort. Turns out that if the array is substantially sorted, it runs pretty fast. And another nice thing about quicksort is that it requires no additional or constant number of extra variables. So there's no additional memory required. And compared to merge sort, well, merge sort run in n log n worst case time, but it requires additional memory. Okay, so quicksort doesn't require additional memory, but we kind of hoping that it's running well. So for good pivots, quicksort is better, but if we're not lucky with our pivots, then merge sort is faster. Okay, here's homework for you. We talked about 4 algorithms: insertion sort, selection sort, merge sort, and quicksort. Implement all of them in C. Actually go there, and write code for each of them. For insertion sort and selection sort, the PowerPoints kind of have the code. For merge sort and quicksort, they are slightly more complicated, but please write the code in C. Okay, that's your one goal. What we're going to do next is, so sorting algorithms are kind of standard, and it turns out that C has a sorting algorithm built in. And the function is called qsort, I guess, for quicksort. And it's included in this stdlib library. And I will try to explain what's going on here. So the signature of qsort, so it doesn't return anything, void. It gets an array. It gets, right, so void pointer means an array. And it doesn't specify which type. It gets n, so n is the length of the array, and I will explain these two in a second. So basically it gets an array of n elements and sort it. But here is the thing. This array can be array of numbers, it can be array of students, it can be array of anything we want. So what size specifies? It specifies the size of an element of the array. And what this thing does, so remember we talked about pointers to functions. So this compare function, this compare variable, it's a function used to compare two elements. And just to say, to tell you something about it, it gets two numbers, for example. It returns something less than 0 if first argument is smaller, namely it should be earlier in the array. It returns equal if the two numbers are the same, and it returns number greater than 0 if the first argument is greater, namely it should come after the second in the sorted array. Let me give you an example. So how should we do it? Maybe we do it actually here. Okay. Okay. So length is just 10. And set rand, it's just a function that sets 10 random values. And here is what we do. Let me GCC use. Okay, so here's what's going on here. So we create a random array, and this part says, print these numbers. So we're printing this array. So this is before. And then we run the qsort algorithm. And after that, we print it again. Okay, so after that, we print, and now the numbers are sorted. So let me tell you what qsort does. So it gets an array. So remember, AR is an array of numbers. So this is the length. If I want an array of numbers, then I type size of int. And the last is this compare ints. So what's compare ints? It's a function that we pass it to qsort. And here is what it does. Qsort doesn't know what's the type. So the function gets, it gets a pointer to our elements. So it's a const, namely that a is not going to be changed. It's a pointer to our element. So we get two pointer, it decides if it's smaller or larger. So first of all, we're going to convert it into ints. Okay, so we're going to say n1 is, take a, convert it into a pointer to int, and then dereference. So this gives us what lives in, the number inside a. N2 is the number inside b. And then what we return is n1 minus n2. Why? Because if the number is smaller, then a must come before b, then n1 is smaller than n2. And if n1 is greater than n2, so this difference will be greater than 0, so it means that b must come before a, or a must come after b. All right. So that was this example. Okay, so we need to write this, compare two elements. And if we know how to compare two elements, then we know how to run the quicksort, because, all the quicksort does is, on a very kind of high level, in each step, it either compares two elements or it swaps two elements. Okay, so we tell it how to compare two elements, and we specify the size so that it knows, what are the sizes that we want to swap. Right. Okay, so this is about the qsort algorithm. Okay, let me give you an example here. So, right, so let's say these are the values. We run qsort, so qsort gets the array. The length is 5. Size of int specifies what's the size of each element, and compare ints, it compares two numbers. So I think this is kind of easier to read, maybe in the code I made it a bit more explicit. So this is, casting a into a pointer to int and then dereferencing, and then casting b into pointer to int and then dereferencing. So this is the function, and qsort, we run it by specifying this comparison. And let me give you one more example. So we don't need to sort only numbers, we can sort, for example, students. So here is what we have. Let's say we have an array of students, and each student has first name, last name, ID, and grade. And let's say we want to sort by grades. So what do we need to specify? So we're giving to qsort the array, the pointer to the beginning of the array. We say what's the size. Size is 180 students. Size of student, this is the size of one chunk. And then we tell them how to compare the students. And how do we compare the students? So we take the first student and the ID, we take the second student's ID, and we do the first minus second. So, if A has a smaller ID, it will be a negative number, so which means A should come first. And if A has an ID that's greater than the ID of B, so A will come after. Okay, so I hope these two examples, okay, one with comparing students and one with comparing numbers, I hope this is clear. Right. So we kind of use this void pointer, which let me try to demystify it a bit. So basically void pointer says, it's a pointer, but I don't know what's type. So basically your responsibility is to tell you what's the type. Right? So if you know that A is array is a student, then you should cast it into a pointer to student. And if you know that A is pointer to int, you should cast it into an int. So let me give you a motivation about void pointer. So maybe I want an array that supports different types. So, I would like to have something like, array of size 3, and it supports a number and a string and maybe, some struct. Oh, that would be really nice. The question, can we do it in C? And we sort of saw that no, we cannot do it in C because in C, when we specify the array, all elements must be of the same type. Okay. We said that, okay, another motivation is sorting things, right? So let's say we want to sort ints or sort strings or sort students and so on. The sorting algorithm is exactly the same. And the only thing that's different is the type inside, which means, uh, how do we, sorting students and sorting numbers is exactly the same thing. If we sort the students by ID, let's say, or we sort strings by some structure, it's exactly the same sorting algorithm. The only thing that's different, we kind of need to write different functions supposedly, but they all do the same thing. So we don't want these. And instead, we want one algorithm that does, sorts all of them, and we only need to specify, oh, you know what, now you're sorting ints, but run exactly the same algorithm. So this is what qsort, so, qsort gave us. It says it's exactly the same algorithm, just tell me what are the types inside and how to compare them. Right. So this brings us to this function void pointer. Okay, so here's what I want. I want to create an array of ints. And then I want a function called print array that basically what it gets an array of ints and it prints them. But then I'll have an array of points. So point is just a 2D point. Okay, so point is, where is it? So point is this. Okay, it's a 2D point. And I want to run exactly same print array function, but now it will be an array of points. But print array is exactly the same thing. The only thing is different. One time it's running on ints and one time it's running on points, but the logic is exactly the same. So what would be the logic? There will be something like a for loop that says, print this. Something doesn't work. Okay. No, something doesn't work. Yeah, everything's fine. So here's what we're going to do. We're going to pass to print array. We're going to print the actual array. Tell me what's the size of each element. Tell me what's the length, and tell me how to print one element. So when printing int, we just print the number. And when printing point, we'll put maybe parentheses and then first number and then second number. So here is what print array does. It says, for each I, print array in position I equals, and then it prints the item, array plus I times the size of the item. So size of the item is the size of int or size of point. So this is print the ith element. We print we run print item. And what's print item? If it's an int, you can imagine just a function that prints int, and print point, it puts parentheses and it puts the first coordinate and the second coordinate and so on. So for print int, it does casting and then prints it. And for print point, it prints these things in parentheses. In parentheses, it says print px and py. So these are the x and y coordinates of our point. So the point is we have this void point, print array gets a void pointer, so it doesn't know what's the type of our array, what are the elements in our type. But whatever the type is, just give me the function that works with this type, and that's all we need. Okay, so I hope this is clear. I feel like I didn't say something or I'm not emphasizing things correctly, but I hope it's clear, at least the code, I hope it's clear what it's saying. Okay, so it gets an array, it doesn't specify the type, so it's just, void pointer. It's an array of elements of unknown type. What we do know is what's their size. We know the length of the array, and we know how to process it. So this is a function that will take one element in the array. Okay, which is, it will get a pointer to the ith element, and depending which function we send here, whether it's print int or print point, this guy is going to run print item on this particular one. And the result is this, so when it's array of numbers, it will print numbers. When it's array of points, it will print points. Okay. And the third example is, so again, think of it as an array, and I want to swap two numbers or two objects in my array, two elements in the array, except that I don't know what are the types of my object. Maybe it's an array of ints, so I need to swap 4 bytes here to 4 bytes there. Maybe it's an array of students or something else. So in general, swap works like this. And it's the same swap, whether it's ints or chars or points or students or cars, whatever the object is, we have exactly the same logic for swap. And the only difference is what's the type we put inside. So to see how it works, let me delete this part. Here is what we do. It's a generic swap, so it gets a pointer to one element, a pointer to another element, and we must specify what's the size, right? Because if we don't specify the size, how do we know is it an int? Is it a student? Is it is it an elephant? We don't know what it is. So here's what we do. We say we allocate using dynamic memory. We allocate s bytes. We copy, so mem copy, I guess copies from A to S. Oh, sorry, from A to temp, it copies S bytes. Then it copies from B to A. So this is copy A to temp. This is copy B to A. And this is copy temp to B. Right. So the logic is exactly the same, but now these are generic types, right? So these are just pointers to unknown types, and S specifies what's the type. And don't forget in the end to free the memory. Right, and there's some small examples here. I don't know. So for example, we have 2 points, and we can print them, and then we can swap the 2 points using pointer to A, pointer to B, and size of a point. So size of a point says, our type is point, let's swap them. And at least let's do this first part. GCC gen swap. And when we run it, so previously, let's see, P1 was 0, 0, and P2 was 3, 3. And after swapping, well, yeah, they swapped their values, right? Because this is exactly what it says. It says move from A to temp, swap between what's written in A and what's written in B. Okay, so this was the first part. And let's try this part. So let's say we have this array 6, 7, 8. So before, yeah, when we print it, it's print 6, 7, 8. And when we swap position 0 and position 1, no, you see, we specify its size of int. So we specify that our elements are ints. So after we get 6 and 7 swapped, let me do one more exercise here, maybe. Let's say it's 9 and 10. And what do you think will happen? What do you think will be the result here? So I'm saying swap A in position 0 and A in position 2, but I'm swapping 2 ints and not 1 int. So what do you think will happen? Okay, so before it's clear what will happen, before it will print 6, 7, 8, 9, 10, and after, and I forgot something. It was so close to working. Okay, what will it do now? So we're printing 5 elements. What do you think will happen? So previously it was 6, 7, 8, 9, 10, and after that it swaps 6, 7 with 8, 9, because we say, start at A0 and start at A2 and swap 2 ints and not 1. So it will take 6, 7, it will take 8, 9, and it will swap them. And I was kind of careful not to make sure that these two don't overlap, because when they overlap, it's kind of less predictable. And in general, we should not, we should be nice. We should not do these kind of things. Okay, so I'll just leave it at size of int, but when you watch the video or you the practice, please uh try different, try 2 times int and see what's going on. Okay. Two more small topics. So I use memcopy. There is something called memmove also. It's a different function. The difference between memcopy and memmove is, so in memcopy, I kind of hinted this previously, the source and the destination, when they don't overlap, we use memcopy. And when they do overlap, it can be kind of tricky. So memmove is safer, but in general, read about the difference between memcopy and memmove. Basically, you should almost never copy from source to destination when they overlap. And when you do it, make sure you know what you're doing, and I think memmove will be your friend. Right, so that's one exercise, and the other exercise is write a generic sorting algorithm, similar to quicksort, write one for insertion sort, for example. Okay, so that will be a good practice, both writing insertion sort, seeing how it compares to just insertion sort of numbers, and two, using these generic functions. Okay, last topic for today. So, okay, this is kind of informal, but I will not do formal proofs here. But we saw sorting algorithms. Can we do sorting faster? Can we do sorting algorithms faster than n log n? So here is a theorem. Basically, if you don't know anything about the array that's given to you, then the running time is at least n log n, and technically it's called the comparison model. And let me skip the proof, but I will tell you at least what's a comparison model. which means basically, you don't have any prior information about the data. So the only thing you have is given two elements, can I compare them? Which one should go first in the sorted array? And let me tell you examples what's not comparison model. For example, if your input is an array of length n that contains all number from 1 to n exactly once, then this can be sorted faster than time n log n. In fact, this can be sorted in linear time. Another example, let's say that I know that my array contains only numbers from 1 to 100. Maybe the array is huge, like 1 million elements, but all numbers are only between 1 and 100. In this case, we can also sort it in linear time, in order n time. Okay, so these are two examples, but unless we know, if we don't know anything about the elements in our array, then for most general algorithms, n log n is the best. And there's no proof here. There's something about n factorial, this total number of permutations, and log of n factorial is approximately n log n. It's not a proof. It's just something that, yeah, these are the ideas of the proof, but I will not say exactly what I mean by this. Okay, so that's all for today. Thank you.